This is Garis MPC, that's Math, Physics, Computing. 130 plus courses in pure mathematics and mathematical physics. This is lecture 4, so MPC 4 on linear algebra at junior and senior level. This is lecture 1, session Y. We are discussing the solved problems, so section 2 of chapter 1 in the text, and the next few questions will be on complex numbers. I need to close the curtains. I'm being distracted by what's going on outside, so just a few seconds. Yeah, that's better. When you're in math mode, you have to be completely left-brained. You don't want to be distracted by other things. Okay, so complex numbers, you'll find this session, the next few sessions, quite a bit easier than the previous one or two, which got quite tough. So question 119, it has various parts. I won't do them all. So I'll do part 1, part 4, part 5, 6 and 7. So left out 2 and 3. So given two complex numbers, you are simply to multiply them. So let's do the reals first. So you get 2 5s, that's 10, and minus 21i squared. Well, I squared is minus 1, so minus 21 times minus 1 is plus 21, plus 10. So 10 plus 21. Now the i's, you get a 6i from here and a minus 35i from here, so it's minus 29i. So you get a 31 here, so the answer is 31 minus 29i. That's not too hard. So part 4, you've given a complex number over a complex number, so a complex number divided by a complex number. So how do you simplify that? How do you calculate what that is? And when you say simplify, you want it in the form of a plus bi. So the standard trick, when you have a complex number that's in the denominator, you multiply top and bottom by the conjugate of the denominator. And remember, the conjugate just means that you switch the I to minus I, so this becomes minus I here. So the conjugate of this is 5 minus 3i, and you multiply that conjugate above and below. And why do you do that? Because when you have, I should put that as a bracket, when you multiply z by its conjugate, so z times z conjugate, the complex terms drop out. They're zero, and you're just left with reals, and that simplifies things. So so let's calculate the denominator. So the reals, you get 25 minus 9i squared, so that's plus 9. So 25 plus 9 is 34. So you've got a real in the denominator. That's simplified things. Okay, now multiply the two terms in the numerator. So the reals will be, so you get 2 5, that's 10, minus 7 times minus 3i squared, so that's plus 21, I squared is minus 1, so minus 21, so you get 10 minus 21, so that's minus 11 here. Now for the complexes, you'll get minus 35i and minus 6i, so that's minus 41i here. And so in the form of a plus bi, so your A will be minus 11 over 34 here. I should be using the black pencil as the pointer. And the complex form will be minus 41 over 34i. Right, part 5 of this question. Simplify I cubed. Well, I cubed is just I squared times I, but I squared is minus 1, so you get minus 1 times I, so it's just minus I, simplifying. Right? So I cubed is just minus I. Now how about I to the power 31? How can you simplify that? Well, I to the power 31 is the same as I to the 30 times I, but I to the 30 is I squared to the power 15, so 2 15s are 30. Well, you can probably see where, why I'm doing it this way, but I'm trying to get I squared so I can substitute that for minus 1. So I squared, that's minus 1 to the power 15, and if this were an even number, I'd get 1. But it's an odd number, so I'll get minus 1. So this here is minus 1. So minus 1i is just minus I. So there's your answer, minus I. Part 6. So you've got a complex number cubed. So evaluate it, simplify it. So, well, that's the same thing as the same complex number squared times itself, right? So let's calculate what this is. Now do the reals first, so you'll get a 1 plus 4 I squared, so it's minus 4, so you get a 1 minus 4. Yeah, here's your minus 4. And now how about the imaginaries? Well, you'll get a 2i from this one and another 2i from this one, so you get plus 4i. So times 1 plus 2i. So this is minus 3 plus 4i here times this. Now, so now we've simplified. Now we're down to just the product of two complex numbers. So let's multiply those two. So what are the reals? You'll get a minus 3 from these and a plus 8i squared. So that's minus 8 minus 3. So that's going to be minus 11 here. And for the complexes, you'll get a 4i and a minus 6i. So that'll be minus 2i. And there's your answer. So minus 11 minus 2i. Okay, part 7. You've got 1 over some complex number, the whole thing squared. So you do your usual trick. You want to make the denominator reals. So you multiply above and below, so this will be within the brackets, and we'll square again later. But so within the brackets we'll multiply above and below by the conjugate of this. And what's the conjugate of this? It'll be 2 plus 3i. So here it is here, above and below. Now the square is outside the brackets here. So now the whole point of doing z times z conjugate, you get rid of the complex terms. They drop out. They become the coefficient of the I is 0. So so you get 2 squared, that's 4. There are no complexes, they drop out, and you'll get minus 9i squared, so that's plus 9. So so you got 13 underneath now, and 2 plus 3i above. So square the whole thing, so we will multiply this by itself, and 13 squared, so that's 169 underneath. Okay, now square this, so the reals, you'll get 2 by 2, that's 4, plus 9i squared, so that's minus 9. So 4 minus 9, 4 minus 9. Now how about the complex part? So you get 2 times 3i, and 3i times 2, so 6 and 12, so it'll be 12i. So 4 minus 9, so minus 5 over 169, plus 12 over 169i. And that's in the form of a plus bi, simple as you can get in complex number. Right? So that's the end of question 119. Skipped a few. Now 122. This is a proof type problem, and I tend to in section 2 on the solved problems, if there's a proof, proofs are usually a lot harder than these sort of simple calculations, and often they're not so obvious, so I put them in. Alright, so you're given two complex numbers, just two random complex numbers, z and w, that belong to the set of complex numbers, so z and w are complex numbers, and you're asked to show, to prove that the mod of the product of these two complex numbers, so the mod of the product equals the product of the mods, in the form of a slogan. Now, what does the mod, a bit of revision, what does the mod of a complex number mean? It's sort of its length. If you think of the Argand diagram, and z is usually expressed to say x plus yi. Now on the Argand diagram, the point in the two-dimensional space, x, y, think of those as coordinates. So your real coordinate along the x-axis is x, and the coordinate along the complex axis, say y, is y. And so the hypotenuse, from Pythagoras' theorem, the hypotenuse, its length, will be the square root of x squared plus y squared. So mod, in other words length, the mod of z, the complex number, is square root of x squared plus y squared. Okay, and we'll use that. Alright, so we have to prove that the mod of the product of two complex numbers equals the product of the mod of the two complex numbers separately. So how to prove that? Well, let z take the general form a plus bi, just a random complex number, and w, another random complex number. So let it take the form c plus di. Okay, and these numbers a, b, c, and d here, they're all reals. They belong to the set of real numbers. They belong to R. Now, to get rid of, now the mod involves the square root. So if we take the square of the mod, we get rid of the square root. It's just easier to manipulate with. So let's deal with the square of the mods, and then later at the end we can go back. We can take the square root and simplify things. But for the moment, it's just easier dealing with the squares. So the square of the mod, by definition of z, is a squared plus b squared, if you square it. Okay, and similarly, the square of the mod of w will be c squared plus d squared. Here it is here. Okay. Now zw. You see, we're trying to calculate what this is. So zw will just be this complex number times that. So it'll be. Well, I haven't written it out explicitly, but I'm just given the solution here. So if you multiply, so for the reals you'll get AC plus BDI squared, so it's minus BD, and for the complexes you'll get BC here plus AD, BC plus AD, and there it is there. Okay, so the mod of this complex number squared, here it is here, that will be just this term, the real term squared, plus this complex term, well, the complex coefficient, if you like, squared. So it'll be that squared plus that squared, which is here. Okay, now it's just a bit of algebra. Just calculate what these. So what's the square of that? Well, it'll be a squared c squared minus 2 ACBD plus BD all squared. And similarly for here, you get a squared d squared plus 2ADBC plus b squared c squared. Now these two are the same, cancel, so just cross them out, they cancel, and so you're left with a squared c, you're left with these four terms. Now these two terms here, they have a squared in common, so take the a squared out, and put c squared and plus d squared in the brackets. And similarly here you've got a b squared in common. So take the b squared out and put the c squared plus d squared in the brackets. Now notice you've got a c squared plus d squared in common. So take that out here and you'll get an a squared plus b squared in the brackets here. Now, what is a squared plus b squared? Well, it's just the mod of z squared. Okay, so mod z squared. And similarly, this is the mod of w squared. So you got it there. All right. So go back to here. Equals. So mod of zw squared equals the square of the mod of z times the square of the mod of w. So therefore this equals this. Here it is written out here. And now just take the square root of both sides and you'll get what you want. So you'll get the mod of zw equals mod z times mod w, which is what we wanted to prove here. And that's the end of the proof. And here is your end of proof sign. Okay? So that's the end of... you may... I guess I changed my mind. I guess I originally eliminated question 121 and changed my mind. So it doesn't matter. The order doesn't really matter a lot. Okay, so now so how many parts in this one? So it's part 1 and part 2, part 3. Okay, so 3 parts to this question, and I solve all of it. So you're given 2 arbitrary complex numbers, z and w belong to complex numbers, belong to C, and you're asked to prove that the oh God, what's the term? I'm forgetting. Adjoint. No? I forget. Yesterday I took possession of a 55-inch 4K computer monitor, and I had to stay up for the delivery guy to come. I had to be there because there'd been a previous attempt missed earlier, and so I'm a bit tired. I didn't get my normal sleep, but the show must go on. Professional. I'm trying to remember the term. What do you call when you do this? Conjugate, right. Okay. So you're asked to prove that the conjugate of the sum is equal to the sum of the conjugates of these two, in the form of a slogan. The conjugate of the sum equals the sum of the conjugates. So in other words, conjugate of z plus w equals conjugate z plus conjugate w. So how to prove that? Well, in a similar approach, it's just basically algebra, sort of. So again, let z just be a plus bi, as you did in the the above question. Let w be c plus di as usual, and these a, b, c, d, they're all reals. They belong to the reals. All right. So conjugate of z plus w. So just plug in the values a plus bi and c plus di for z and w here. So you get this, and rearrange a little bit. So bring your reals together. So a plus c. You got an I in common, so take the I outside and into b plus d. So you rewrite it that way. Well, now you've got the conjugate above. So just conjugate this term. And remember, to conjugate simply means to substitute minus I for I. So this I here will become minus I, as here. Okay? Now, so you will get A minus BI. So just rearrange terms a little bit, and you will get C plus minus DI, C minus DI. But what is this? This is the conjugate of Z, right? Because here you got minus I. It's the conjugate of Z. And similarly, this is the conjugate of W. So the result is conjugate Z plus conjugate W here, as was to be proved. You had to prove this, right? So end of proof sign. You finished your proof. So part 2, you're asked to prove that the conjugate of the product equals the product of the conjugates. So, which is sort of analogous to here. Here you had the conjugate of the sum equals the sum of the conjugates. Here you've got the conjugate of the product equals the product of the conjugates. Right, so it's similar. So we'll start with the left-hand side. So the conjugate of the product, so you just plug in the values for Z and W. So here, that's Z and here's W. Plug them in. As here, now just multiply these two complex numbers out, and you so do the reals first. So you get AC plus BDI squared. Well, that's minus BD as here. Then for the complex values, you'll get I times BC plus I times AD, which is here. Okay. So this is now just a simple complex number form. So we can now conjugate it. In other words, we just change this I to minus I as here. All the rest the same. Now this next step is a little less obvious. You may say, where the hell did that come from? Now remember what we're trying to prove. We're trying to prove that the right hand side is a product of two things. So we need to convert this into a product of two things, because that's what we have on the right hand side. That's what we're aiming towards. So this, if you give it a little bit of thought, is actually equal to this. Now that's not so obvious, but you're motivated to create some kind of product, of two terms, because you want to get this. So if you look at this, you'll see that it is this. Okay? But what is this? Well, A minus BI is just Z conjugate, and C minus D is W conjugate, which is what you wanted to prove. That here is the right-hand side. So the conjugate of the product equals the conjugate of the product equals the product of the conjugates. And that's what we wanted to prove, so end of proof. Okay, part 3. This one's pretty easy. You're asked to prove that the conjugate of a complex number is just a complex number. In other words, these two conjugates cancel each other in a sense. Well, pretty easy. So Z is just A plus BI as usual, but with a double conjugate, so two bars above it. We're going to conjugate the conjugate. So let's use the lower conjugate. We'll do that first. So that will convert this into a minus BI. Remember, conjugate just means convert, change I into minus I. As simple as that. So you get this, and then we conjugate it again, so the I becomes minus I. So you'll now have minus B times minus I. Well, that's just plus BI, but that's just Z. Okay, so the double conjugate of Z is just Z, as was to be proved. So end of proof. Okay. Now, that's the end of the session. I'm just going. Tired. I was just going to go straight on, but this is a new section, and as in the previous board, I now the next session is to the right of a left-hand one. So I move horizontally. I don't move vertically. So I'll stop here. Ciao.